get started. I see some familiar names in the participants, and I'm glad to see you here. So my name is Yang Xu, and I'm an assistant professor of computer science in SDSU, and I run the lab of computational linguistics and cognitive sciences. So maybe I can talk about why I'm doing this seminar talk. So our group, our lab, have a regular meeting every week, Friday morning. So basically we meet on Zoom and talk about the progress on our research projects. And so machine learning is basically a tool that we use a lot, and particularly for language tasks. So you may have heard hear the terms like natural language processing. So that is basically the research area that our group is in. So I found that the PyTorch is a kind of tool that is very suitable for carry out academic researches. It's like not a heavy tool. It's a pretty lightweight, although the ecosystem is very large. So that means there are plenty of choices of little toolkits that satisfies the goals as a researcher that basically wants to deal with all kinds of machine learning tasks. So that's why I found necessary that maybe we can have a short introductory level to this powerful tool. So although when I was making these slides, I just realized that the ecosystem of PyTorch is just so large, and well, maybe the machine learning area is also a gigantic area now. So we basically need to have some preparation knowledge in order to understand the paradigms, the programming styles, the language, the grammar, like the grammar quoted, like how the code are organized in such a way in machine learning projects. Okay, so I just found that there are so many things to do. So I really want to make this tutorial or this introductory talk to be simple enough, but also it should be comprehensive to some degrees, so that you will have an idea of what kind of things, what kind of tasks can be done using PyTorch, and what kind of interesting functions that PyTorch provide in terms of designing a model, in terms of processing the data in an efficient and interesting way. Okay, so yeah, so I will get started right now. Okay, let me close the participants window. All right, so a little bit about myself. I am currently an assistant professor. So I did my PhD training in Pennsylvania State University. And my research area is natural language processing. And the research questions that I ask are usually the intersection between psycholinguistics and cognitive sciences. So machine learning is one of the computational methods that I use in my studies. And I'm interested in the short-term adaptation and the long-term changes in human languages. And the most recent projects that our team is working on is about the multimodality nature of human dialogues, especially when that dialogue happening online, like what we did right now. Although this talk is more of a one-way broadcast of information, but if it's a conversation, then there's back and forth, like people taking turns to make meaningful utterances, and that is the case that we want to study. So our current goal is that we want to have a system that can more intelligently understand the intentions of speakers in the online conversation, in particular within the context of online education, like within the class, how likely is the students going to speak, and whether the students' intentions are fully understood by the teachers. Okay, so the languages and the speakers' behaviors are the subjects that we are interested in. So all these behavioral patterns in human language and human behavior can be modeled by machine learning models. Okay, so that's why we use machine learning techniques heavily in our work. Okay, so what is PyTorch? PyTorch is the topic, the main focus of the talk today. So it is a open sourced library, or you can say it is a computational programming framework, okay? And it is used for applications in computer vision and natural language processing. And it is developed by Facebook's AI Research Lab. And I think it is released in the year of 2016. And actually, this idea of PyTorch is based on an older software or older framework called Torch. And Torch is written in another programming language, Lua. But at that time, at the year of 2016, even earlier, Python already has a very good ecosystem that supports the data science tasks or scientific computation in a really good style. So that's why people find that using Python could be a better choice than using another using Lua as a language of relatively small population. Okay. Oops, what happened? Okay. So PyTorch is a Python-based programming package, and it is basically tailored for two sets of audience or users. First of all, it is a replacement for numpy, so that it can utilize the power of GPUs. Okay, so numpy is an even earlier software that are first developed in the context of scientific computation, especially for spatial data, like the galaxy data, like the and the large scale geography data. Okay, but the shortages of numpy is also very salient, and we will talk about this in later slides. That it can only handle process data in GPU, but in the era of deep machine learning, there are just so many matrix multiplication, matrix level operations that can be accelerated by GPUs. So that's something numpy cannot afford. And PyTorch provides a big advantage over numpy. And also, it is a deep learning research platform that is very flexible and provides and runs in a very good speed. So this is more a comparison with another well-known package called TensorFlow. Okay, so TensorFlow is also a package that is particularly designed for deep machine learning or deep learning. But maybe I can say something about TensorFlow 1.0. So now we have TensorFlow 2.0, but that is the first release of 2.0 is early this year or the end of last year of 2019. So before that time, it's the time of TensorFlow 1.x. And I personally don't like the style of TensorFlow 1.0 because it is not eager execution. Or so the variables you design need to be put under some well-structured computational graphs, and it's not easy to look at the values of those graphs because you need to first open a session and run the variables, and only in that way you can check the values. So which makes the development of your code and the debug of your code not as straightforward as PyTorch does. So PyTorch is provides a more dynamic environments, and it's just like a Python. So everything can work within a Python interpreter. Like you open Python, and nowadays I guess people will more likely use the IPython or Jupyter Notebook. So in those cases, you just import Torch, and then you can play around with the tensor variables in Torch. You can look at the values of it. Like after initialize some random tensors, you can look at the values of it. And maybe after a for loop with some iterations, you can quickly check the values of those variables. Okay, so yeah, that's what PyTorch basically does. It is a machine learning framework, programming framework, and especially tailored for GPU use and for building large deep learning models. Okay, and it's easy to install. It's like just install some third-party Python packages, and it's also easy to play around with PyTorch. So you basically open up a Python interpreter and you import Torch. So you may notice that here the package's name in pip, it's Torch. It's still Torch, and when the thing you import is also still Torch. So I guess it's a convention following a very original version of it, which is written in Lua. The name is Torch. Okay, and you can look at the version of your PyTorch basically in the Python interpreter, and all the functions, all the examples provided on the official websites, and all the examples that I'm going to show in the slide here, you can try them in your interpreter, and the results will basically show up instantly if your code is not complex, if you don't define some insane looping code to train a model or something. Okay. All right. So the main outline is listed here. So I'm going to go through some important concepts in PyTorch. First of all, tensor, and I will talk about what a tensor is and what do we do with tensor, and secondly, I will talk about the model. So because the talk is for a guide to machine learning, and a machine learning task needs to build models. Okay, and the data, the third-party data, because data is kind of the fuels that we need to feed into the model, and the power to shape to tune the parameters of the model. Okay, and in particularly, I will talk about a third-party package which is whose name is transformers, and this package is very well developed, and it saves time, a lot of time for natural language processing tasks, because it provides predefined models. And these transformer models is not like closely coupled with PyTorch, because it also provides APIs to TensorFlow. But I think the style is, the very original transformers is based on PyTorch, and it also utilizes a very dynamic programming styles. And yeah, let's talk about tensor. But before that, I would like to have a simple mind model of machine learning here. So this is the image that I use in the CS 596 machine learning class that I'm teaching. So I think this is a quite the simplistic mind model to understand what we are doing in a machine learning task. Okay, so in the middle, within this red box, we have our model. Okay, and the model is a collection of parameters, and those parameters are to be tuned in a way that it can succeed in some tasks of doing the classification or regression. Okay, so that is the goal we want to achieve. We want the model to make some predictions or make some classification, to accomplish some classification task upon some new data. Okay, and how do we achieve that? We need to train the model by feeding it sufficient amount of data. Okay, and basically the more data we have and the higher quality data we have, then the model will tend to behave, will tend to perform better on the new data sets. Okay, so a good machine learning framework, programming framework, should handle or should provide help to all steps that are involved, included in this pipeline or mind model of machine learning. Okay, so first of all, the first thing we can think of is how we represent the data, how we put data into, or how we load data into computer memory, right? How we represent the data with some data structure. So we need to use tensor. And for the models, when the models is big models, large models, the number of parameters can grow insanely fast. So, and that's why we also need to store those, the parameters of the models in some data structure, okay? And turns out that everything that come with a number. So all the parameters and data, they can also be stored and be processed within this data structure called tensor. Okay, and it is the tensor is the idea that is originated from the mathematics. So you can think of it as of a higher dimensional matrix. Okay, so a two-dimensional matrix. Matrix is a two-dimensional data structure. Basically, you have rows, you have columns, and tensor is like something you can add one more dimension to matrix. You have a cube, right? So the cube is a three-dimensional tensor, but you can also add another dimension, which makes it a four-dimensional tensor, and that is hard to imagine because we can only visualize 3D tensors, limited by our brain, but it can be handled by a computer in a computational way. Okay, so it's basically a n-dimensional array. Okay, if you have used the numpy before, then it is quite similar. So judging from the appearance of a tensor, it's quite similar to the numpy.ndarray. Okay, so like if you define something that has 2 columns, 3 rows, and 5 layers depth-wise, so you have a 2 by 3 by 5 numpy array. Okay, so that's something you can do in numpy and put each grid or put each each element a random number. Okay, so this numpy statement initialize a 2 by 3 by 4 5 array with random numbers, and you can do the same thing in PyTorch. So you just call torch rand number 235, which specifies the dimensions. So if you give the same seed to the random number generator, so the resulting A and B will be basically have the same values. Okay, and PyTorch provides an easy way to convert a numpy array to some tensor. Say you have some numpy array created here, and you can easily convert it into a torch. So it basically provides a wrapper around the numpy array. So this is a quite common practice, because if you have some experience in numpy and other data science packages like pandas, so they are quite lightweight tools that help you load data and reshape data sets really quick, right? But after you have loaded data into memory, before you feed it into a machine learning model, and if your machine learning model is built using PyTorch, then the inputs need to be a PyTorch tensor. So that's why you need to basically convert the numpy array into a torch tensor before you feed it to the TensorFlow, before you feed it to the PyTorch model. Okay, so that's why this step is quite often used. Okay, but what I want to say is that the tensor actually does way more things than numpy array. Okay, so numpy is just a framework for scientific computing. It does not know about the workflows of a deep learning, of a machine learning task. Like, it doesn't build a computation graph for you. It doesn't know about the gradients. Okay, so gradients is something we use in machine learning to indicate the amount of change that each parameter needs to make in order to achieve smaller or lower loss between our prediction and the actual outcome. Okay, so this gradients is a term to refers to that little amount of change to the parameters that we need to make to tune the parameters. Okay, so we'll look at the difference using a set of simple examples. Okay, so if in numpy we want to define a simple shallow 2-layer neural network, okay, then we basically first define the data. Okay, and that's the X, that's the input data, and the Y is the output or the label. Okay, that Y is our label. So they are the shape of the X and Y, they are n by d in and n by d out. So basically we have n training instances or n training examples. So the first dimension is the number of examples, and the second dimension d in here, it is the size of each data instance. That is basically the number of features, right? So, and the d out is the number of predictions the model need to make. Okay, so if it's a simple 2-layer neural network, then we can define the weights like this. The weights, they are no more than matrices. Okay, so a weight for one layer neural network. For the first layer, its dimension is d in by h, and h is some number of the, we can decide it is the hidden, it is the size of the hidden layer. Okay, and this d in, let me use another color. This d in must match with this d in because W1 is where the input X is fed into the model. Okay, and the second weight matrix W2, it has same hidden size H, and the output size D out matches the size of the label. Okay, so that is two matches we want to make. So how do we make this shallow neural network work? Is to do the forward pass and the backward pass. Okay, so in the forward pass, it's quite straightforward dot production because given the input X and the parameter W, you basically want to compute the hidden by making the dot product between X and W1. Okay, and that hidden needs to be fed into a ReLU, an activation function like sigmoid and ReLU, but in this case we use ReLU, so we achieve that by calling this numpy.maximum function, and the final prediction is the dot product between the hidden activations and the second layer weights W2. Okay, so that's how we get the prediction manually in numpy. Okay, so that way, this forward step is still straightforward, right? It's and intuitively easy to understand. But the thing of manual computation is the backward step. Okay, the backward step means that how do we get the gradients for each parameter given the loss between the prediction and the y. Okay, so in shallow, in neural network, we basically use the backward propagation algorithm to compute the gradients for each parameter in each layer. Okay, so that is basically a chain rule we need to follow, right? So we need to go from the prediction to the parameters in a backward style. So we have the loss as the difference between the prediction and the y, and then we need to compute the gradients for the prediction first, and we plug in that gradients to compute the gradient for W2, right? And then we also compute the gradients for the HReLU and the H and gradient for W1, like in this backward style. So that's how we get the gradients. And only after all the gradients are obtained, we can then update the parameters. And as you see, this is a very time-consuming step. Okay, so that's why we, in PyTorch, we can, it automates everything about gradients. Okay, when you define the tensor, so this is the same as the x and y's, and here it is also the same shape tensor, but with this statement, with these arguments specified. It says that for W1 and W2, because they are weights, I need to know about their gradients. So that's why I said requires grad to be true. And the default values for this parameter, for this argument is false. So for x and y, because they are data, I don't need to know, I don't need to change them. So I don't need to know about their gradients. So the gradients will not be computed for them. Okay. So here with this requires grad to be true satisfied, then we can simply compute the gradients by calling this loss dot backward. And loss is defined in the forward step, right, by computing the distance between the prediction and the label y. Okay, that is the loss. In this style, the loss is similar to the mean square error loss for linear regression. Okay, and the forward step also becomes more compact because the grammar provided by PyTorch. So this one is the first layer, and this is the ReLU activation, and this is the second layer. Okay, and the thing is, the critical step of doing the computation of the backward step is done by the loss.backward. Okay, so that is something provided by Torch that we don't need to worry about the details. And then what happens after this function is called? Okay, so if we look at the W1 and W2 again after this function is called, then we will find that we can access the grad, which means the gradients attributes for these two tensors. There's something computed and stored in these attributes. And then we can use these gradients to do gradient descent. Okay, and gradient descent is a way that we update the values of the parameters. Okay, we basically want to go against the direction of gradients. So if we do that manually, we need to subtract the gradients times some learning rates on top of the original values of the parameters. Okay, so one thing we need to notice here. So first of all, we need to, after we update the parameters, we need to set the gradients to be 0 manually after we have updated weights, because then after this iteration, there will be the next iteration of gradient descent. And the second detail is that we put these 4 statements under this no grad context, because we don't want gradients to be automatically computed for these updates operations, right? So these are not part of the training. These are just they are the outcomes. They are the necessary steps after we have obtained the gradients. So we need to simply update the values of the parameters, but this is not the computation that we need to compute the gradients. So when we update them, we need to put them into no grad. Okay, so here's just some technical details, and we already see that the convenience way of using PyTorch against the numpy, but it can do furthermore actually. Okay, so in the next topic, we're gonna see in our definition of machine learning models what numpy can, what kind of convenience that numpy can provide. Okay, so let's continue the example here. PyTorch provides a module called NN, which is for a neural network, and there's a whole lot of different models defined in this model, and it is very useful to build large-scale neural network models. For example, we can put the different modules in a sequential, wrapped by this sequential module, okay? And the first layer, the first component of this sequential module is a linear layer that has the D-in as the inputs and H as the outputs, followed by a ReLU activation, and followed by another linear layer that has D-out as outcome, okay? So this much more simple form is, or much more easier to read, is the same model that we defined using numpy and torch tensor manually. Okay, so here we're not using torch tensor, but we're using modules provided by NN. But it provides a more convenient or more compact way of defining models. Okay, and also we can use the loss, predefined loss, instead of doing the computation manually, like subtract y predict with y raised to the power of 2, something like that. We simply call this mean square error loss and specify the reduction method to be the summation. And that's how we define the loss function and the model. And the model and the loss function here, they are all callables, means that they can be called with data as inputs. Okay, so if we look at the example next, the model can be called. So when after the model is defined, we can feed it data simply by call it and feed the data in, and it will return the prediction from the last layer, which is a linear layer. Okay, and for the loss, it's also a callable. We can call the loss with two inputs, which is our prediction and the y, and it will automatically do the mean square, error, and summation computation for us. Okay, and what's left is gradient descent, and we can simply call loss dot backwards, and then we again use the, well, here I didn't say that we need the step of loss dot backward. Okay, so that backward is still necessary. Okay, and after the backward is called, then we need to again use a, under this no gradients context, we need to update the parameters manually. For all the parameters in the model, we'll do the gradient descent, and then we will zero the gradients, the gradients. Okay, so that's how the same task can be achieved with the NN module. Okay. Okay, so here there's still something manually done within this gradient descent. So PyTorch provides another wrapper, which is in the optim package, which is for optimizing. So it makes the training step easier because we don't need to define, we don't want to manually update each parameter. Okay, so this time we define the optimizer, which is an atom optimizer that takes the inputs. Okay, so this inputs, this parameter tells the atom optimizer that I want to optimize these parameters with these learning rates. Okay, so the returned optimizer will simply can zero the gradients for you, right? So this time we will call the optimizer.zeroGrad. And again, more conveniently, after the loss.backward is done, we can simply use optimizer.step. Okay, so this .step function basically does the manual gradient descent, basically does the manual gradient parameter updates for you in the previous example shown here. Right, so everything within this with no grad, with the for loop, can be done automatically with the simple function step. Okay, that is one more thing the torch can, one more convenience the PyTorch provides. Okay, and that's one example using the NN module to define the very simple neural network model. But we know that nowadays the models are huge ones, and we need more flexible way to define and adjust models. So that's why we need to use the NN module in a more custom style. Okay, so for example, we can define the two-layer neural network by making it a subclass of torch.nn module, and we need to basically define the constructor here, which tells that we have two layers, both of which are linear layers. Okay, so that is the initialization step, and the forward pass behavior is defined in the forward function here. So this forward function takes inputs the data, and it computes the forward. It implements the forward data path for you, like the forward pathway for you, like it calls the linear and the ReLU, right? And it computes the outputs and it returns the outputs. Okay, so that's basically the for loop, the forward function that you want to write for each custom module you wrote. Okay, and after we instantiate the model, right, we initialize the model and we call it just like the way we use before when we use the NN.sequential, right? And this paradigm is highly flexible. You can put everything you like into the members here. The member modules are not necessarily linear. It can be very complex ones like a RNN cell, a RNN model, a LSTM model, or a convolutional neural network CNN model. So everything can be put here. You can put multiple neural networks. And in the forward, you can define how those models are combined, how the intermediates representations are taken out and concatenated and added to each other. Do everything you want to do. So this is where the real magic happens in PyTorch, that you can, if it allows you to design everything in a very flexible style. Okay, so that's the model. So let's look at what complex layers or what complex models are already defining and that you can pick up and use. So these are basically the very convenient off-the-shelf units you can directly use in PyTorch. First of all, a recurrent neural network unit. Okay, this is the very efficient implementation that takes inputs, a sequence. Okay, so this input is like this three-dimensional tensor, and this first dimension is the length of your sequence, because RNN models deal with sequential prediction. And the second dimension is the batch size. So we're using mini batch gradient descent. Then this batch says each time we have 3 input instances. Okay, and the 10 here is the input size. So this 10 must measure the 10 here, because when we define the neural network, the recurrent neural network, we need to specify the input size. And the 20 here is the hidden size. Okay. So, and the 2 here is the number of layers. So we can have the hidden layer outputs like this for each layer, for each hidden units, and for each batch instance. Okay, so we can directly have the outputs by call these RNN units. So RNN is a highly complex structure if you want to implement it manually, because the backward propagation, you need to do a very use a for loop to do the backward propagation, which is just tricky. But in RNN, in PyTorch, it provides already ready to use package for you, so module for you. Okay, and for LSTM, it is just another advanced version of neural network style module, which requires the definition of two types of hidden units, one for the gate and one for the hidden representation. So similar operations can be done, and similar outputs can be achieved. Okay, so these are the modules we can very easily use in under this NN module. Okay, so I have more examples here. For example, in natural language, because we are representing word with a dense vector, so a lookup table is always necessary when we want to see what the vector is for a particular word. So the embedding module provides such a function. When we divide the embedding table, we need to specify how many words are there, how many total vocabulary are there. So in this toy example, we have 10 words in total, and each word is represented by a vector of length 3. Okay, so when we give it an input with this long tensor, so this long tensor is a 2x4 matrix, right? After we give input to the embedding objects, the returned embedding vector is 2x4x3. Okay, this by 3 is that we return the vectors for each word in the input. Okay, So each word, the vector for each word is returned here. And here, these are just random vectors, but these embeddings vectors can be trained. They are the parameters in our model. Okay, so here's just another example showing what NN can do. Okay, so one more extreme example here is the NN dot transformer. Okay, and a transformer is a very complex model that stacks multiple layers of feed-forward neural network, self-attention, and the normalization layers together as a very powerful encoder model for textual data. Okay, so PyTorch provides such a many hierarchical modules. So this NN transformer refers to the whole model here, which I wrote in blue, and the transformer encoder refers to the left parts. Okay, and the transformer decoder indicates the right half, and the encoder layer is just one layer within the encoder. Okay, one layer, and the decoder layer is just one layer within this decoder. Okay, so these are very hierarchical structure here, and you can notice that there's an n times here, right? And this n is usually like 12, 24, and even higher in design. So, and then dot transformer provides a way to manually build such a model. Okay, but in practice, unless you want to train a transformer model totally from scratch, then you will need to use these layers. You will use these modules. In other cases, we usually download the pre-trained models and just use the output layer of those models. Okay. So anyway, before these models are provided, if you want to write the model on your own, there's a lot of boilerplate code you need to write. So using the code here, reuse the code here definitely saves you time. Okay, and allows researchers, scientists to think about interesting questions, but not need to worry too much about the underlying implementation. Okay, and not just for NLP tasks, but the CV tasks, computer vision tasks are also well supported by PyTorch, and this module called Torch Vision. So this is something you want to install independently. It is not Torch, but it's Torch version, but it's developed by basically the same team now. Okay, and it provides a lot of CNN-based models that supports basically the full range of CV tasks, like image classification, object detection, video classification, and so on. And any models you can name it can be basically found in the models here. All right, so much about model. I will try to finish within 10 minutes, okay? It's longer than I thought. So data, all right, because remember the mind model we have, once model is defined, we need to have a mechanism to slice the data into pieces and handle and feed data into the model, okay? So those data sets are really critical to the training of models, and the existing data sets are all available, provided in Torch Vision datasets, and this is particularly for computer vision, like the well-known MNIST for handwritten digits detection, and ImageNet for object detection, right? And for the NLP tasks, we use torchtext, okay? And it also provides a way to load custom datasets, okay? For example, if you define the datasets in this style, you tell where the dataset is, you tell the dataset's name, so the results can be, the file can be a 2-column TSV separated by a tab, within that file, there's within each line, there are two columns. The first line is the text. The second column is the label, right? Text, label, text, label. And that's how you organize everything within the TSV file, okay? And after you have stored the data in such a way, these tabular data sets will makes the data sets a iterable object in Python that you can access each row very quickly using an integer index, okay? And it gives the fields to the first column, right? The fields of the first column is text, and the second column is the labels, okay? So you can access them with these keywords, okay? And one more important thing is that it helps pre-processing the text for you. It can load the pre-trained embedding for you, and it also support various ways of mini batching operations that are designed for different tasks. Okay, like for language model, the way mini batch should organize is different from a text classification. Okay, and if we look at the data, the data set function module provided by Torch, we can define a custom data sets. Okay, so in this simplistic example here, we tell where the actual CS file is, and after we initialize it, in the initialization of the data sets, we read it using pandas, and then within the get item function. So this get item function is basically the way that we want to tell the data set to return when we give it its index. It will read the image, right, given the name, and return the image into as a key value, okay, as a dictionary, as a key value within a dictionary object, okay. So that's a lot of flexibility here. And I see a question. I will answer the question later after the talk, and we're reaching the end of the talk, okay. So that's custom data sets. So with this custom data sets defined, we can load any kind of data sets, like any kind of data set in such a format, just like the way we use for a Python list, right? We can simply view face data set as a Python list that we can access its ICE index. Okay, and for data loader, it's a higher level wrapper of data sets. The primary goal of it is to provide very quick and easy automatic batching for you. Okay, so we can set the batch size so that after the data loader is defined, if we iterate over the data loader, what we get is not a data instance, but a bunch of instances in the batch here. Okay. All right, that's and the mini batch is critical in deep learning because if we take everything into one training iteration, that is not possible when your data set is too big. And a proper definition, a proper choice of mini batch size will result in a reasonable convergence speed when you train your model. Okay. And lastly, we are here talking about transformers. I am hoping that our lab members, our students in our lab can read more about the transformers model, because this is the kind of the state of art in natural language processing, and also it is critically important when we build future multimodal models. So these transformers is a third-party package. It is not the same thing that we talk about in torch.ndarray. No, it's not this thing. Okay, it is a it's a plural form, so it's include the multiple models. it provides general purpose architectures like BERT, GPT-2 for natural language understanding and natural language generation, okay? And it provides pre-trained weights so that you can directly download and load it without training from scratch, okay? So now let's look at the example of BERTs, okay? So BERTs, the pre-training, first of all, the hierarchy of the model BERTs itself uses multiple layers of transformers. Okay, so within these the blue circle, it is a transformer layer. Okay, so BERT actually is a huge model. It uses the basic version uses 12 layers of transformers and transformer encoder layers, and the larger ones has 24 layers of transformer encoder layers. Okay, so you basically use multiple layers of transformers to obtain a very contextualized embeddings for the word inputs. So here in the red rectangle, these are raw word embeddings. Like the word embedding is trained from word2vec or from whatever kind of word vectors. So these word vectors, they are fed into the transformers so that the contextual information are also modeled. So the T's here, they have contextualized meanings. Okay, like the words, even the same word within different context, the differences can be captured. Okay, and actually this one on the left is the inputs to here. Okay, so this one is input to here, and the outputs layer on the top of here, these layers, they are used to complete some task called mask language tasks. So we basically mask some inputs tokens here, like randomly mask them here, and use the rest of them to predict those masked tokens. So this task is used to pre-train the BERT model. And after the model is pre-trained, all the parameters in those transformers, they are fixed, and we can use this fixed representation to get a well-contextualized representation for basically any kind of input sequence. Okay, so when BERTs is applied to text classification task, say given a task, given the input sentence, we want to classify whether it is spoken by a human or a robot. Okay, say that's something we want to do. And then we basically feed that input sentence into the pre-trained BERTs, and we get some final the last layer outputs, and we use some certain token label to as the input of our predictor. Okay, so basically we can use the pre-trained model from the transformers. So transformers is a package, third-party package. We import some particular type of model. In this time, we want to use the sequence classification model, and we load the pre-trained weight like this, right? And then we'll need to use the outputs of the model to make predictions. Okay, so the model will take input IDs and generate some outputs. So the outputs will be just the last layer of the BERT model. Okay, so within the training of the classification model, we usually just don't need to update all the parameters in the BERT. We just update the last layer of it, because there are just so many parameters. So one thing I didn't mention here is that these BERTs or transformer models, they are all very large models, and they can have tens or hundreds of millions of parameters in it. So deep learning is not cheap, and that is also a concern that we need to deal with, because training such large models, it costs electricity, costs time, costs money, and we don't want to. We want the scientific research to be sustainable and also to be meaningful, instead of just stacking insane amounts of models, but didn't care about how we explain those models, right? Yeah, that's the example of BERT for classification. So for summary, this is the final slide. So we talk about the model, data, third parties of PyTorch, and hopefully this tutorial gives you a broad introduction to the tool, to the ecosystem, and so that you know what kind of tasks that PyTorch can be used to do. And hopefully this is a good pointer that leads you to the ocean of the large ecosystems of PyTorch. And they're way more interesting stuff than what I have been talking about in these 60 minutes today, okay? So I'm going to look at the question now. Basically, integration of torch vision and torch text we can use to handle multiple data formats into one-dimensional format and numpy, so like n-dimensional array, which can handle multiple data types like video data, audio data, text data, image data. Let's say one row for image representation, one person, one column, textual information. Yeah, that is basically true. So that's also something we are doing right now. That's the question I type it to everyone. So right now in the data sets, like say we want to model the sentence. When I say some sentence, I want to tell what my intention is. So the sentence, the language in the sentence alone provides some information, but also my gesture, my facial expression, my sound, right, my audio, they are all the features that belong to this sentence. So we can basically put them in a row, right? We can, for example, the first column is the collection of images or video clips of my gestures. The second column is my facial expression, the joints of my facial components. And the third column is the audio signals. The last column are the language, the words, transcripts. So in that way, we basically can view each row as a very hybrid data instance, okay? And that is something can be achieved by the custom data sets provided by the PyTorch. And so building such a model will on the one hand, it utilizes more information from multiple channels. So the resulting model should have higher intelligence in predicting human behaviors. For example, if you know my facial expression, you're gonna know better about what I'm gonna say in the next few seconds, compared with without knowing my expressions, my non-linguistic signals, non-linguistic behaviors, right? So yeah, that's a good question. So I'm happy to take questions, and I want to thank you for coming to the talk today. And this will be a very useful tutorial for everybody, and I will upload it to my YouTube channel. Yes. So if like the way we did for the example we shown here, right? Maybe I can, sorry, I can return to the slide here. Right, so if I use this example, we define the data sets and we load all the landmark frameworks into this data sets. So that is okay, because the CSV file only contains the name to the PNG file, to the image file. So the images are not actually loaded, only the names are loaded. So only when you want to get the certain item, you will need to read the image here, right? So that's kind of a trick that saves the memory for you. So if we want to design a large data set, that's basically the principle we need to follow. We don't want to stick everything into the memory. I see another question. When we mention PyTorch makes better use of GPU power, does that mean it will be better useful for computer vision applications, comp data, let's say like astronomical numpy? Yeah, so basically what we do in PyTorch, sorry, I mistyped. I want to send this to everyone. For example, the matrix computation, the way you define the neural network models can be achieved by numpy. That's correct. But numpy itself is not, it's not a tool designed to like do gradient descent, to do deep learning training. It's not designed for that. It's not that goal. Its goal is more at the lower level in handling data, in process data in a efficient, fast style. So numpy is not suitable for carry out machine learning tasks. And when I say PyTorch makes better use of GPU, because PyTorch wraps up the numpy data sets and makes them can store them into the GPU device. What I didn't say in this tutorial is that PyTorch provides an easy way to migrate data, to copy data from CPU to GPU and GPU to CPU back. Because when you want to do the forward pass, you want to put everything into the GPU, okay, because the computation is over there. But later on, once you want to write out your data to disk, then you will need to move out the data from GPU to CPU. And the batch data is in CPU, because when you load the data into memory and you put it into a loop, like when you iterate over a mini batch, say in this page, when you enumerate your data, the sample, the batch here is in GPU, it's in CPU. So before you want to put it into a model, you want to, first of all, move it to the GPU part. That is the current limits of our current computer architecture. And this gonna probably be solved in the future, like more data transformation, better data transferring speed, and so on. My YouTube channel, let me see if I can quickly copy it right here, YouTube. My channel, oh. Maybe if you search my name, if you search my name, oh, wonderful. Thank you, Phillips. Yeah, that's my channel for, I upload my, all my course videos to that channel. And if there are no more questions, I'm gonna end the meeting here now. And I really appreciate everybody coming to the talk, and I hope this talk will be helpful to you and bring some new thoughts to you, and maybe opens up new directions, no matter whether you are interested in machine learning or you just want to know something cool, something new. And I'm glad to talk to you guys. And yes, thank you. And have a good day, guys.